afternoon, and welcome to the Department of Medicine's Grand Rounds. Please take a moment to silence your pagers and mobile devices. Grand Rounds next week will be presented by Dr. Paula Rosenblatt and Dr. Brian Barr on the field of cardio-oncology. Today we will be having an Institute for Clinical and Translational Research talk presented by Dr. Anupam Joshi, the Oros Family Professor and Chair of the Computer Science and Electrical Engineering Department at the University of Maryland, Baltimore County. Dr. Joshi is also the director of UMBC Center for Cybersecurity and one of the leads for the National Cybersecurity federally funded research and development centers. Dr. Joshi obtained his Bachelor's of Technology degree from IIT Delhi in 1989 and a master's and PhD from Purdue University in 1991 and 1993, respectively. His research interests are in the broad area of network computing and intelligent systems. His primary focus has been on data management, security and privacy in mobile and pervasive computing environments, and policy-driven approaches to security and privacy. He has published over 275 technical papers, been granted 9 patents, and has obtained research support from the National Science Foundation, NASA, U.S. Department of Defense, IBM, Microsoft, Northrop Grumman, and Lockheed Martin, amongst others. Speaking to us today on medicine and computing, please join me in welcoming Dr. Joshi to the podium.
Thank you very much. I'm delighted to be here and really pleased at the opportunity to, I'll get all my gadgets right eventually. Really pleased at the opportunity. Thank you, Dr. Davis, for the invitation. I talked to some of my colleagues that I've worked with over the years to find out what this audience looks like, and it's a mix of faculty and students and residents and so on and so forth. So I'll keep this general. My aim is to make sure we develop further collaborations between medicine and computing, which I think are required to solve some of the challenges in the future. The particular things you'll hear are completely incidental. They're anecdotes, they're stories, so I'll say a little bit more about that. So I don't know if the residents or the students are supposed to fill out some kind of a form at the end saying, I attended this talk and this was, I was asked to give CME learning objectives. So if you sleep for the rest of the talk, this is the too long, don't bother version of the talk. So I'll talk a little bit about UMBC and the new core we have set up in ICTR around sort of AI, cyber, things of that nature. And then I'll go through some projects that we've done with School of Medicine and BA, with the hope that you take away 2 messages. One, some problems are relatively straightforward applications of the research that has already happened in computing to a medical domain. You get together a group of people, you hire a master's student, they download some standard software, boom, it works, right? But for a lot of the really challenging things, you see some examples, you need clinicians and computing professionals to get together and think about what might happen, what the challenge is, why the problem is important, what new techniques. It's not just taking existing stuff in computer science and applying it, it's developing brand new techniques that are published in computing literature. So these are the projects that mostly I have worked on. There are many examples, including examples where I have worked on that are, if I started fitting everything, so just last year, Professor Shin and I had a collaboration to develop a survey instrument to understand security of medical devices, not covered here. So there is a lot of stuff that's happening between these 2 campuses that I'll only cover just some vignettes. So I'm now going to tell you about UMBC. It's a sister campus. Hopefully you know something about it. But I did want to point out that at the institutional level, when we look at the research themes, security, AI, cognitive, analysis, and health ID are the top things you see under the computing board. So it's not just because I'm giving this talk to you here. These are slides from my vice president for research. So I didn't make them tailored to this talk today. This is the talk that our vice president of research gives no matter where he goes. And we have a deep partnership already at the level of the 2 presidents. There is a great desire for more faculty to work together. Technically, those of you who are faculty here and people like me are all colleagues in the University of Maryland Graduate School of Baltimore. neither university has its own graduate school. We have shared graduate school. So there are good touches and overlaps, but we need to see more happen. And we're doing great work in cybersecurity. I won't bore you with it, but as you begin to think of your research, often the colleagues working in medicine don't think about security. It's someone else's problem. Regrettably, it is not. Regrettably, as people are discovering that this is a vector of attack that they can use to bring down societies at large, not just steal some information from a computer. This is going to be increasingly important in your domain, and I'll say a little bit more about that. And we certainly do a lot of work in analytics. There's this huge NSF-funded IUCRC, so-called Industry University Collaborative Research Center. There are only a few of these in the country. We're one of them, and our focus is on analytics. And again, this is a slide meant for general audience, but notice that healthcare is front and center in what we present to the outside world. Again, I will not talk to you about ICTR, but what we did was we took Dr. Davis's nice diagram and added a circle to it. So the Cyber and AI core is now an integral part. I think it was officially announced last week or 2 weeks ago or something like that, but it's a very integral part of the setup. And as you work through that institute, those of you who work through that institute, we are part of it and are happy to collaborate. My colleague, Tim Oakes, the professor in the Department of Computer Science, will serve as the lead and will spend time here physically, significant portions of his time to make that work. And we have a website. So I was giving you examples of the kind of things. So security in medical devices are things that colleagues like Professor Shen from the School of Nursing already do. Think about it. Right? You're putting an infusion pump. Can I have that? But you are building an analytical model. Right? How many of you have heard of something called adversarial learning? Anyone heard about that buzzword? It's all part in the computing industry right now. It's like the big thing. You stick adversarial learning in your paper, and it gets accepted. I'm kidding. We're not that fickle. But what adversarial learning is how many of you have seen those algorithms from Google and all, which can you give it a picture and it tells you what the picture is? And you've seen all of that stuff. Google has been great about it. Well, guess what? 2 years ago, Google published a paper that showed that if you add additive white Gaussian noise, so those of you who still remember your statistics course will know what that is. If you add additive white Gaussian noise into that picture so that it looks completely not different to a human being, just looks like the same picture, Google will take a tag and recognize it as a panda. When you can fool, the worst example, a highly cited paper that was published, not by us unfortunately, but some colleagues in Rutgers last year, was this. All these self-driving cars that are coming out there, they have these image detection algorithms that can detect the road signs. So what these guys did was they took a stop sign and they put a post-it note strategically on that stop sign. And guess what? These recognition algorithms, these models that have been built and trained on data, sound familiar? Lots of data, models you're building, training on them. Well, they're so brittle that this algorithm now said, oh, this is a 45 mile per hour speed sign. Imagine what would have happened if this was a deployed system. So as you take lots of data and build models of predicting this, you'll see examples of this, looking at genomic data or star-omic data to predict disease progression. You're inviting an adversary to treat that data very slightly for a patient and have you make a completely incorrect decision with your CBS system. So security is something that I encourage you to think about much more than you have, but it's not the central focus of my talk today. Professor Grasso is here, so we already had an existing collaboration. There's a clinical informatics group where we do a lot of stuff. What I want to talk about is we play with lots of data, and we're right now working on a brand new project to look at opioid prescriptions. So there's going to be a student from UMBC working with Professor Grasso. Okay. So now I want to give you an example of a problem that required joint work between computer science and medicine, and some of you will recognize your colleague Elliot Siegel from radiology. Right? And again, these are all published in computer science conferences, so the titles are all in a way that a computer science reviewer will accept. Right? But this is how I would put it to a medical audience. And to illustrate it even better, this is from VA. The patient and all have been blanked out. In fact, you'll see a fake patient name appear on the next screen. But this is from VA, right? How many of you deal with these kinds of notes in your regular practice? Presumably almost all of you, right? So the particular patient whose notes, de-identified notes we were given access to, was a case of renal abscess, 1 month on and off interactions. At the point of the 1 month where they came for their next consult, there were 650 such pages. Now imagine you're a clinician. How many of you, okay, maybe you won't answer this, but I ask you to think about how many of you will read 650 pages of notes carefully to figure out exactly what happened, right, before you make your, I don't know how it works in the hospital, but when I go and see my GP, he probably has 15 minutes to see me. It requires more than 15 minutes for him to read 650 pages of notes. So I can guess what happens. Now the idea was, the challenge we were given by Elliot was this. He says, can you take something that looks like 650 pages of this, and I apologize, the diagram doesn't come across very nicely in a slide, but go here is, as this is unfolding, right, over a period of time, the size of the circle will tell you, and this number here tells you how severe the pain was, the subjective pain rating given by the patient, and this tells you the location of the pain. And you can put in other things. The other thing we wanted to do but didn't fully get to do was making this clickable. So you can actually click on this and the right note will pop up. So suppose you were curious on what happened between this point and this point, that you went from a pain of 3 to 7 and then it shifted from the shoulder area to the abdomen. So you could just click and the notes would pop up. And the other thing we failed to do, and I'll tell you the challenge of the problem, so I hope you don't think, oh, this was trivial stuff and they failed to do it. We failed to do was fully being able to extract what prescriptions were being given at the point of care when this was happening. But the idea is you want to go from 650 pages that look like this, that no clinician will have time to look at, to something like this, which a clinician can glance and get a very good sense of what happened. So it turns out that you can't do this with state-of-the-art computing tools. And I would tell you this, that these are great state-of-the-art tools developed in the national security domain to read tons and tons of textual reports and make sense out of them. So this is fairly sophisticated work, but it doesn't work, right? Because the assumption of most of this is that text looks like this. Text does not look like this in clinical note CMRs until it has gone to someone whose job is to look, or is basically transcribed. So this happens much later. But if you look, this is the STEMEVAL challenge in 2015. For those of you who play in this space and have looked at I2B2 data and others, they all look very clean and grammatically correct like this. So this is an example of a particularly good note from the VA. Right? Less than 5% of the data, there's a paper in 2008 in Anya, says that less than 5% of the data on a clinical note looks this clean and grammatically correct. So the entire suite of algorithms in natural language processing that assume that you're reading text in English suddenly crash and burn. Because you're reading text that is probably English, but it's not the English that you expect, right? And it's not just a VA problem. This is NHS in Britain. And okay, I hang around with doctors, so I know a proton pump inhibitor and an H1 blocker when I see it. But I looked at this and I have no idea. Some of you may, what OOHD means, right? Okay, full confession, I also know that diclofenac sodium is NSA. So, but again, I hang around with doctors a little bit more than an average person. So this kind of grammatically incorrect, weird notations, weird shorthand text, and you'll see this example later for the abbreviation RT. If you found the abbreviation RT on a clinical note, what would you guess that to mean?
Respiratory therapy.
Anyone else?
Right.
Okay. Respiratory therapy, right? Okay. So if we do a survey, we'll probably come up with at the last count in NIH's system, there are 37 expansions for RT in a clinical setting. Now again, we as human beings are extremely good at looking at the context of the discussion and say, RT shoulder probably means right shoulder, not respiratory therapy of the shoulder. But to get it computed to that state requires significant advancements in the state of the art. So this is a good example of the kind of things we want to do. So for those of you who have a computing background, the kind of text you get from the VA or NHS or whatever fails in the fundamentals of the natural language processing pipeline. You can't figure out what the sentence boundaries are. You can't tokenize, you can't do part-of-speech tagging, you can't parse it, you can't recognize entities. Right shoulder might be written as RT SHD. SHD is, again, could expand to so many different things. You don't know what you are talking about if you're a computer. And we just talked about the heavy use of abbreviation. So this is a challenge in computer. It's certainly a challenge in medicine, taking clinical notes and making sense out of them. But it's a challenge in computer science. I can't just say, let's take the state-of-the-art algorithms and run them, because they will fail. We tried that. So what the impact is, as I was telling you earlier, paper by Kulakov, 95% of the text in the largest healthcare system in the US will fail going to work with existing tools. So what we did, and I'll give you, again, this is not a talk of NLP practitioners where I'll get into details of exactly what we did for the algorithms and how we made it work, but I'll try to give you a hint of the kind of things you have to do. So the first thing is you have to come up with something called an ontology. So who still remembers what an ontology is from their philosophy class back in the undergraduate days? Anyone? Okay, if I was just asking you what an ontology was, forget philosophy. Like, think of SNOMED CT or UMLS. Those are all ontologies. So ontologies are a description of things that are and the relationships between them. Right? So it's a description of the state of the world as you see it. And so we created an ontology, and again, we were focused on pain for this particular task. You'd have to do something similar if you were doing a different domain. But we said, look, pain has symptoms, pain has severities, pain has a duration, pain has an onset, pain has a location. So we came up with this kind of an ontological guide. If you would, this is now what is giving us some context on what we are doing. So the corpus we worked with came from Elliott, the identified corpus with a variety of different, so just so we didn't bias it to a certain single kind of event, an issue that was causing pain, you can see there's some of the appendicitis, syncope, perineal abscess, hypercalcemia, colon cancer, just genetic idiopathic pain, anemia, lung cancer, etc. So, so there's all different sources from when pain would come. we had these clinical notes, and our job was to say, again, can you go from, so what I showed you was the end product of our research. Can you go from those notes to something that looks like this? So about 93,000 lines with clinical notes. And what we want to do is, in addition to identifying whether there is pain itself, whether this note talks, some part of a note, some sentence talks about pain, we want to identify certain attributes of the pain. And then this talk, I'll focus on a couple of different attributes and how we did it. So pain has a severity, pain could be negated, patient says there is no pain, etc. kind of thing. Pain has a location, pain has temporal concepts, onset, duration. Pain has quality and type, and I won't even try to explain what that is because I'm in front of, if I was in front of a computer science audience, I would have tried to say what these things mean, but I'm not even going to try with you guys. So just to identify pain itself, so just to give you a sense of why that task is difficult, the note could say pain or painful. That's easy, we can get. But the note could say odynophagia. Am I saying that right? Which means that's a pain happening when certain action occurs in an implied location. So if you say, look for the occurrences of pain in the clinical notes, you're going to crash and burn. Because you'll miss this, right? You'll miss some obvious abbreviations. There are specialized terms. They have to be up on your Greek and Latin and so on and so forth as an NLP, because you could be talking, the note could be talking about myalgia, which again is a pain, but it's applied in the construction of the term, and its location is identified in the construction of the term. And there are things like headaches and so on and so forth. So it's actually very complex. It's not just a matter of looking for occurrences of things that say pain. Just to give you a sense of this is a non-trivial task. So what we had to do was to develop a specialized pain lexicon. We mined UMLS and Snowbird CD, develop this lexicon, and now we were able to do fairly well. So here are the examples of things where we did well. This is the obvious one. Patient states that they do have pain. Yes, state of the art would have picked this, but denies any focal weakness or headache, denies any. I'm not sure what FC is. Say again?
Chills.
Okay. So we can pick up implied pain here, we can pick up implied pain here. So we can do a reasonable job with the algorithms we built of taking this non-obvious stuff and making it a meaningful extraction. Where we failed was, so sometimes the clinical notes will have these kinds of hypothetical statements, right? So we would say, oh, this was talking about pain. No, it was not. It was talking about the possibility that pain may have. And for reasons that I don't want to go into technically, the fact that things are not structured as clean sentences, are broken across lines and all, does like a lot of damage. If folks would just enter full sentences, or at least not break lines at random places when they're entering notes in the EMR, you do all of us a huge favor in terms of recognition accuracy. Oops. On this one we failed because there was a weird line break, and on this one we failed because there was no gap. So the tokenizer failed to see this was pain, and then 7 to 8 out of 10. It just looked like a single phrase. Could we fix this with a hack? Yes. Would that be a general purpose solution? So the other example I want to give you is location, which is actually very tough, and the state-of-the-art algorithm, the one that before us was doing the best of this task out of Mayo Clinic, completely failed. Just not being able to extract stuff, right? So as we said, some locations are implied inside the pain term itself. There are weird uses of where nouns should be used, adjectives are used and things like that. Again, the clinician is not thinking about grammatically correct text when entering stuff. But not all locations are anatomical. So you could say there is pain at the site of the incision. It's not an anatomical location. So if you just try to go with anatomical stuff, you fail. And locations can act both as targets and modifiers of the pain description depending on the context they're in. Okay, this is, I think, what, and since I don't have my notes in front of me, I forget whether this is UMLS or SNOMED, but this is what they say the location should be described as. These are just some of the descriptions we actually found in the clinical notes that all meant to say right to a quarter of the arm. Here is a similar example of both shoulders and arms. If you go by the standards, you guys should be writing your notes to look like this. This is what you actually write. At least this is what the VA doctors actually write. I don't know what. Yes, sir.
Have you compared dictated notes versus written notes? Because it looks like that there is the problem.
That's a part of the problem, right? So you're right. There is a ton of literature before us that looks at the cleaned out notes and works well on that, right? But at point of care, you often don't have that transcription done, or you may not often have that transcription done. So the challenge to us from our colleagues in the VA was, can you make sense of this? So we're trying to, and again, that's an interesting challenge, right? I don't know how much cost you pay in the transcription process, but if we were to get algorithms to work on the non-transcribed text,
It's much higher, but it's more expensive.
So anyways, just an examples of abbreviations and variability of expression. So what we did was we started with the foundational model of anatomy. Is anyone familiar with this? It's the structural informatics group at University of Washington Hospital. Does that. So, oops.
You got hacked.
So it's a, yeah, maybe it's your computer, so I don't get hacked. So it's a formal ontology, so it has relationships. You can, so for example, you could say that the right leg is a part of, the lower extremities. So we can actually draw inferential relationships like this. If a physician says, was there ever a case when this person presented pain in the lower extremity and the note actually said pain in right leg, we would have said yes. We would have reported that up. And there are about 80,000 anatomical terms in synonym. This is what it actually looks like. So we built on that. We used this. We ingested this knowledge that the University of Washington folks have kindly built over the years. Okay. But the foundational model of anatomy, and don't criticize me for it, I didn't build it, it's the University of Washington folks, your colleagues, or had at the time we did this research about a year and a half ago, no concepts for bilateral, right, for side of body. It had no plural forms, it was a hand, you put down hands, right? It had no abbreviations that looked like this, and it certainly had, obviously it's a foundational model of anatomy, so it had no sense of non-anatomical sites that would present pain. We also looked at the NIH specialist lexicon, and this is what I was talking to you about. So for those of you, I don't see respiratory therapy here in their top 5, but you can see a bunch of others. There's 35 in all for RT. So we again mined this information and put this into our system. And again, this will sound like magic, and I'll leave it at magic for now. If these words occur in the sentence, it was not talking about pain. Just, it's magic. The person who did this now works for an agency that is relatively close to UMBC, dealing with problems with national security. We can get her here and tell you why these things work. For whatever reason, they're indicative of a sentence not talking about me. And this will make sense to you. This will make much more sense. these kind of words cannot appear as singletons. So when we are doing the parsing, we just see right, it's not talking about pain. Right has to be followed by some part of the anatomy to make sense about talking about pain. So what we built them, the system with all these pieces of knowledge to solve these problems, to find all the words that appear in the specialized location alignment, ignore them if they are only single terms, filter out certain terms that are not indicative of pain, and attach it then to a sort of saying, is there a pain mention within a certain window of words? And if so, this is what this is talking about. So we were able to do good stuff, right? We can pick this location, we can pick this as a location, we can automatically infer a location by looking at this or this. We can identify non-anatomical locations, and again, we can identify the locations in these kinds. So we do a pretty good job of actually reading this text, and you'll see the composite numbers at the end. But sometimes simple things trip us up. So someone misspelled extremity, and then we fail. Here is another example where the pain reference occurs too far away for our context determination to see that this pain is associated with what these numbers are associated with this pain. So we, of course, formally evaluated this. I'll just run through that very quickly to give me time to talk about a couple of other things. And I won't tell you about annotation processes and things like that, but we had 3 clinicians, very experienced. Interestingly, so what you're giving them is you're giving them some of these notes, the training version of these notes that I had already identified and said, mark out everything, wherever there's a sentence, say whether it talks about pain, and if it talks about pain, say which of these attributes it talks about. So the clinicians were asked to produce sort of a gold corpus that we would run our tests against and train our system. And I will tell you that there's a measure called Cohen's kappa of something called inter-annotator agreement. In other words, you give the same notes to 2 clinicians and say, tell me if the sentence is talking about pain and where it's talking about. The agreement was only about 60-65%. So it's not the case that and again, these are extremely experienced clinicians. So with respect to first-year med students disagreeing on something is one thing, 2 experienced clinicians disagreeing. But nevertheless, for a lot of things, we were able to get them to about 70% agreement. That's good enough. In published literature around natural language processing, if you get Cohen's kappa above 0.6, you're good to go. So we just managed to reach that. So forget weighted versus unweighted, but these numbers look good, which is the idea that we are able to pick negation 97% of the time, we were able to capture the severity of the pain 95% of the time, so on and so forth. And if you compare this, so I'm comparing it against a previous task. This was an open competition. Unfortunately, we couldn't get data back and forth, so these numbers have to be compared with some sort of grain of salt. But notice this was on a completely clean, the kind of text we were talking about, so things that have been transcribed and cleaned out grammatically. And we were able to get, slot accuracy is basically saying there are 6 or 7 attributes. For a pain occurrence, were you able to get those attributes when they were present, right? Essentially, that's what slot accuracy is. And we are able to get slot accuracies better for this kind of completely unprocessed text than text that was completely clean. So again, notice this was an open, challenging problem in computer science that required computer scientists to work with clinicians to make this work. It wasn't just take some existing toolkit, download it, run it. Now I want to give you a different thing. This is it's like that one was only about 1.5 years old. This one is much older. Some of the older physicians in the room might remember Dr. Adrian Park. Anyone here remember Dr. Park? Yeah, so just a few. And Jimmy Lowe was a resident. And the one great achievement of this project was that I can say cholecystectomy without stopping. It took me a while, certainly did. So the idea was, and I'll run through the slides, but in the interest of time, I want to give you the big picture first. So, TATRIC, anyone here funded from TATRIC? Army Research Materials, Medicine, Command, Fort Derrick. Used to give a lot of funding to UMB. Anyway, they came up with this idea of something called trauma pod. This is, a few years post the Iraq War, where the idea was that the medic corps was now good enough that for 90-something percentage cases of battlefield trauma, they would be able to, stem the bleeding and make the soldiers, the warfighters, stable enough to be evacuated. But for the remaining, 5-7% of the cases, TATRIC was envisioning that there'll be a robot. One of the armored personal carriers will have surgical robots that will be wheeled out. The surgeon would be back in the field hospital, and they would operate and take out the bullets and stabilize. Right? So you can imagine, very futuristic, forward-looking. This was when the Vinci robot had just, the surgical robot had just come out. So we're talking about 8 or 10 years ago now. Now, anyone else here from the School of Nursing? Yeah, I know. Anyone else? So the doctors may not appreciate it. For the people from the School of Nursing will certainly appreciate it. The thought of all the program managers was the hotshot surgeon who was going to be doing this thing. They forgot that in any successful surgeons, there's like the perioperative. There's about 8 or 10 perioperative folks, including people who know what the surgeon's pick list is. That was news to me, by the way, that there is something called a pick list, and surgeons are finicky, and if it's not their exact pick list, they're not going to do. Any surgeons here, I apologize in advance, but that's what I was told. So, simple stuff. How many sponges were taken out, and how many of them are back in the trash can right now? Because if their numbers don't match, then guess where the sponge is before you sew the person out. Right? Giving the right instrument to the surgeon, understanding what state the surgery is in. Again, it's a lot of support stuff happening. So they built this robot, and then they didn't think of anything else. So then we started this collaboration with surgery, saying, can we bring in AI and machine learning and things like that to essentially fill some of these nurse roles? Right? Can you identify what stage the surgery is in? And unfortunately, living in Baltimore, there are good approximations to the Iraq War. So the case we took, Dr. Joshi, you would appreciate this, is blunt force trauma leading to hypovolemia, attention pneumotherapy. You can figure out person's been shot scenario. Right? And we said, if a surgeon is at Tamimi, can you figure out what stages are happening? And essentially generate the medical encounter record on that. So, given time. The idea here is that a modern operating room has a lot of devices, sensors, tags, smartphones, monitors, whatever. Right now they exist as isolated units. Can you get them all to collaborate and talk to each other? In particular, in our case, we actually had robotics sort of surgeons. So the surgeon was remote, but there were surgeons approximating the nurse who were physical, right? So there was no nurse remotely operating them. They were supposed to automatically figure out the next tool from the pick list that the surgeon would need is X, and have the robotic arm out with that tool. So we were building the AI, if you would, to make this happen. So the idea is that you need to understand the context model to manage the resources, and you should be able to have the intelligence to recognize events and activities in the presence of noisy, incomplete, or contradictory data. If anyone in computer science tells you that this is a solved problem, they're citing a mistake. This is an open challenge. It has been an open challenge for 10 or 15 years, will probably be an open challenge for the next 10 or 15 But the idea is, can we make incremental steps in solving particular versions of this problem? So can we take the operating room version of this problem and make attempts to solve it? So again, this was limited by the tools of 7 or 8 years ago, but the idea was that the medicines would be barcoded and scanned before, the nurse would scan the thing before giving it to the physician. Staff would, this is when UMB was thinking of the next generation of their badging, so I don't think they went with it. At that point, there were serious discussions between the CIOs on RFID versus ZigBee versus whatever. But the idea was that your badge, as you walked into the room with your badge, the room would know that you were there because your badge was being recognized. So you would recognize staff, you would recognize tools, RFID tags on tools to recognize what particular tool is. And now this are open problems in computer science. Something called continuous querying. And the easy way to figure out is this. And I'll give you an easy version of the problem that's easy to understand. The problem is actually very challenging. The easy version of the problem is for certain cases of, I think, depression medication, you can't give NSAIDs concurrently with MA, forgotten the abbreviation now, I apologize. MA?
MAO inhibitors.
Yes, MA, right. So this is what the surgeon would say on top, right? This person, this patient coming in is patient suffering from depression, is on MA inhibitors, no NSAIDs allowed. The event scanning that you would get at the lower level, so this would be a standing query saying, whenever this event occurs, alert. And data is just flowing through, tons of data from a lot of different places. But if you think about it, what would be scanned was that ibuprofen was being administered, right? Or diclofenac was being administered, or naproxen was being administered, right? There is now an inferential step that we can easily make saying, and again, going back to the ontology, there is a relationship. Ibuprofen is a NSAID, so the alert should fire. Right? But again, getting that computer to do this for non-trivial cases of relationships is not easy. This is an open problem that's very hard to address, and a lot of us have spent time trying to do this, but we built a version of the system that used simple is-a relationships in the operating room, but the idea was to say, can you take patient histories, medical supplies, staff information, active stuff that is coming in saying who's in the room, who's out of the room, who's next to the patient, and what medicines are being administered, and then have some continuous queries. And in our case, the continuous query was what stage of surgery is the patient in? We skipped all of this, but the idea was to generate a medical encounter record, and I have a clip of the video sort of there on what was done. This is technical detail. So we used the, at that point, this was brand new, the human patient simulator from many. Anyone here worked on the human patient simulator? Okay, the surgeons at that point were trying to move away from the each one, teach one kind of thing to saying there'll be all this simulation geovisity that you would train on before you do the surgery on the pig, before you do the surgery on the human being. So we, sorry. We used blunt trauma, multiple injury, essentially someone being shot with a bullet, right? And then these are, as you lose blood, you have hypovolemia, which can lead to tension pneumothorax, and then you do decompressions and fluid infusions. And again, you wanted to recognize as the surgery was progressing through these stages, you wanted to, the continuous query was what stage is the surgery in, because that will inform what the nurse robot was going to do, what tools it was going to present, what things, right? So we mined the sensory data, and believe it or not, we mined the messages that these robots were sending to each other on the network. So machine-to-machine communication was mined, right? To come up with this stuff, and we were able to get this with a very, very, very high accuracy. You can see, so this sort of is in the middle. And again, this is dated. Those of you who are Mac aficionados will recognize this is what a Mac looked like about 8 years ago. Events going through, medicines going through, who was the anesthesiologist, who was the surgeon, and so on and so forth. as well as some vitals that will be monitored, because for certain things like hypovolemia and all, the vitals are an important way of telling you that the patient has gone to that stage, and then the idea was there will be some video. This is a completely unrelated video. The idea was there will be video. Okay. So we'll stick to surgery for a few more minutes. Any surgery residents here? No surgery residents, all right. So, and again, I know all of this second and third hand, so please correct me for any those things. But when you do a lap cholecystectomy, the most common mistake made by trainee surgeons, which can prove fatal, is to cut the cystic artery. So it flows through near the liver and the gallbladder. So the first step that the trainee surgeon is told is, thou shalt create this clear field where you can clearly identify the bile duct, the gallbladder, and cystic artery. And then and only then shall you proceed towards the next step of the surgery. So the question for us was, these surgeons were training on simulators, we were getting the video from the simulator. The way the process worked at that point was then the attending would have to look at these videos and say, oops, you made a mistake here, right? The idea was, can you get an AI that will look at these videos and say, the trainee made a mistake here, here, and here. So the first task we did was essentially, and this is where this is a version of the problem where you can take existing stuff, standard machine learning, SVMs with linear kernels, for those of you who are familiar, and make it work. So the idea was, can you identify, I don't want to tell you what this is because you guys know this better than I do, but the idea was, can you see that the site is being clearly identified before the tool goes in? By reading the video, and it turns out that we can actually do this very well. By looking at 6 features, around 90% of the time, we're able to correctly identify when the trainee was making a mistake. Okay. I only have 9 more minutes and probably 30, 40 more slides, so so clearly you're going to get short shrift on this part, but I hope I've given you some sense of an easy problem and 2 hard problems. This is a hard problem, right? From a computer science sense. It sounds very easy, which is this. There's tons of, how many of you read every piece of literature that is published in your subspecializations? I don't. Right? So what happens is periodically there are Cochrane's reviews and things like that, where some people will take it as a task to read all the papers published in the field over the last 10 years and say, well, okay, the standard treatment for H. pylori suspected infections should be a PPI and I think it's a mix of 2 antibiotics, right? A fluoroquinolone and a macrolide. Yeah. So, okay. That's because they read like a bunch of papers and said this seems to work best. And I think the argument that in the Cochrane review I remember reading was whether a 3-day course is sufficient or a 7-day course is needed for H. pylori. And I think the consensus there was 3 days was sufficient. Right? That's an old Cochrane review, so who knows what's going on right now. But what is critical is, all of this information is in tables that look like this. If you could only get machine intelligence to make sense of these tables and interpret them automatically like we do, and combine them, you won't need doctors to do Cochrane reviews. Doctors would be helped. Every published paper would be fed to this AI, and periodically would come new treatment recommendations saying it looks like based on what people are publishing X. Turns out it's an incredibly hard problem. And to show you it's an incredibly hard problem, I will, so by the way, the meta-analyses are published at a relatively low rate. So I just want to tell you that how many of you can look at this and figure out this is about basketball? Oh, please. So more hands should go up saying you figured out this is about basketball, right? And why do you figure that out? Why is this about basketball? Take guesses. Teams names, okay, but these could just be cities. Why do you think these are team names? These could be cities. Chicago is a city, Philadelphia is a city, Houston is a city, San Antonio is a city.
Names and positions.
Hmm?
Names and positions.
Names and positions. Positions is perhaps one of the most uniquely identified things because, believe it or not, there is a very famous Michael. If you were talking Michael Jordan to a computer scientist, they would think of this very famous professor in Berkeley. You find it in artificial intelligence. So, yes, computer scientists can be weird like that. Right? We don't think of number 23. But this is giving you the cue. This is giving you some cue. Although again, you are queuing on the titles, which make sense to you, but they don't make sense to a computer. A priori has no idea what height means. So you have to train. So the idea is this is a simple table. Right? Now I'm trying to imagine the type of tables that talk about intent to treat, number to treat, what dosage was given, what medication was given, how long. It's much harder to handle than this. So we started with something simple like this, and the idea was, can you automatically connect these to sort of a machine understandable reference? This is to URIs from DBpedia, which is the, let's say, the computer understandable analog of Wikipedia. And can you identify the relationships between these columns? So the medical tables are harder because there are row headers in addition to column headers, and there are virtually no strings where we can make sense. It's like everything was numerical, right? So it's much harder to make sense, and a lot of information is buried, and there are like custom formats, like things are written like this, which is mean followed by the standard deviation. And a lot of the information that would normally be in the table is actually implicit in the caption of the table. So you actually have to factor in the caption. Yes, this was the study, I think 7 or 4. Believe it or not, we built a system, and there's no time to talk about the technical details. It's a very, very, very hard technical problem. We were able to do a good job with this, to read some, and again you can see things like UMLS and so on and so forth appearing. So these were the papers. There were 4 papers with some tables around thrombosis, so that was spontaneous or secondary and all. We could actually be able to make reasonable sense. I'm just going to skip through this. So basically the idea was we were actually able to say what was the percentage, what was the mean, what was the standard deviation, and what concepts were being talked about, whether it was out of ecology or it's our custom system or UMLS. So when you say hypertension, which of these concepts do you mean? So we were able to build sort of this kind of system where you would say, well, show me what papers have talked about this issue and what the tables are, and it will pop the tables right back up. So I'll just say that the precision and recall were 0.7. So precision measures how accurate you were of the things you retrieved, right? Were you actually talking about hypertension in this column or not? Right? If you said this column was all about hypertension, that's precision. And recall is of all the columns that were talking about hypertension, how many columns did you correctly identify? So that's recall. And so you can see these are pretty good numbers. And I'll skip this and leave time 2 minutes for questions. And I'm happy to hang around after that if there are any questions. But I appreciate your coming here. Thank you so much.
Thank you, Dr. Joshi, Professor Joshi. Wonderful talk.
You didn't talk about it, but is your group active in computer-assisted clinical decision support?
So the answer is complicated. The short answer is yes. The longer answer is typically in collaboration with colleagues like Dr. Grasso or Dr. Siegel and others. In other words, we don't go off on our own and do clinical decision support. We build the tools that are required for clinical decision support, and we then try to work with physicians to actually solve a challenge.
So in that vein, if you were presented with an algorithm for management of a disease process, okay, would you, let's say, develop a system whereby a clinician who's seeing a patient and the patient is at some stage in their condition, could they, use a system where they would identify what would be the next appropriate treatment they should use for this patient?
Yes.
Rather than having to put in a consult to a specialist.
I would, okay, so I would not venture so, because that would require FDA approvals and good things like that. But can we build a prototype system which would demonstrate capabilities like that? Yes, assuming the right sense data or the clinical notes were available, right? In fact, Bruce Gerard was working some years ago with a colleague of mine to do this, where even the GP consult was being replaced by this question answering system that had a deep model of gastrointestinal diseases. And so yes, those kinds of things can be done. You would probably have to be specific. You can't say for any, in other words, you can't replace a clinician today. You can't say for any random disease or for any random progression, walk in and the computer will tell you what the next step is. But if you said for patients being seen, so we work with Dr. Grasso for patients who are presenting in ER with chest pain, right? And as you know, there are the syncope number calculation and the San Francisco number calculation. They're basically standard questions that you ask in a workflow, and then based on that, you either tell the patient to sit and give them an antacid, or you wheel them in. But can you do a sort of an automated version of that in more complicated scenarios where there isn't a straightforward question? If you go through the short answers, yes. And we'd love to explore this idea. Yes, sir.
Thank you so
Yes,
much
ma'am.
for your wonderful presentation. I have a question about the pain ontology.
Mm-hmm.
I could have missed it, but was there an attribute acute versus chronic, or is it different? Does it require different?
I think that was in, I'll show you the ontology offline, right? I think that was in the pain quality descriptor.
Oh, okay.
Thanks for your talk.
Sure.
It's really amazing what you've been able to do from natural language processing.
I appreciate the language.
standpoint, but I appreciate the complexity of what you're trying to do, and but we're really trying to gather meaningful data from a sort of a hodgepodge of word fragments and thought processes placed in our own personal format that helps us, that may not be necessarily easy to extract those data. Should we instead be sort of flipping this question on its head and saying, instead of trying to extract these data from a flawed system, and it's kind of, we're in the future, and really where I think we should be is, shouldn't we be designing systems that not only don't necessarily put the onus on us to enter the data correctly, but actually streamline our data entry, but in a way to collect those meaningful data in a way that
So that's a very perceptive point, and I noticed that my GP about 3 years ago when I went to see him last was no longer writing down free-form notes. Yes, I'm supposed to see them once a year. Apparently, it turns out if you're a man and you pass a certain age, your disease risk just like double, for no good reason except you pass a certain age. Anyways, so yes, I've just committed heresy by seeing a senior physician. What I noticed even 3 years ago was that he had a tablet, and he was not entering free-form notes at all. Everything was a checkbox or a button tick. Now, this is outside my domain of expertise, but we have colleagues who work in human factors and human-computer interaction and things of that nature. But I think I'll flip this question back on you. Would you prefer a system like that, where you were guided and constrained by the computer on what you could and could not say? Or would you want a free-form system? So for me, yes, getting data from something like that would be much, much easier problem. But would a physician or a clinician want to do that? That I don't have the answer to.
Well, I think from a pain location standpoint, let's say, or severity, whether it's a Likert scale or you tap on a human figure, say here's the left shoulder, you tap on that, and it can be process to geographic.
Certainly those systems are relatively easy to build using state-of-the-art technology. In fact, the VA system, I think, had them. And again, I hate to bring out these kinds of distinctions, but the notes that the nurses were supposed to be entering used that. So you saw those sections where there was like pain, location, blah, pain. Those were nurses' notes. And the clinicians' notes were much more free-form. Yes, sir?
I'd like to just expand on the discussion, I think, which is fascinating, and your talk is just unbelievable. But really looking at human factor engineering user interface, I'd really, maybe have you look at getting the information directly from the patient, so that they can sort of use an interface where they can feel like their story is well captured. And, that process is everything, and it eliminates the constraint of the 15-minute visit, because, patients can certainly enter that information in a user-friendly interface while they're waiting to be seen, and all of that already compiled in a usable format.
Great perceptive points, and it points to the issue I was raising earlier, which is you need sort of a close collaboration between clinicians and computing professionals. Because left to our own devices, we will say, what's the most challenging natural language processing problem that could exist, and we'll try to solve that, right? Because I want to publish a paper when I want to get tenure. But for those of us who are post-tenure, we can afford the luxury of saying, I will work with a colleague in medicine and publish in a medical journal, which no one in computer science cares to books it. Right? Again, just trying to bring out the realities of cyber life. But that's I think an excellent point, and I think it points to the need for collaboration, because I wouldn't have thought of that, but you would.
Okay, last two questions, back and then.
Thank you so much. Regarding the pain question, I love the way you did the external validation, but there's some opportunities for internal validation with, like, if there's pain score recorded in the chart, as there often may be, or if there are ICD-10 or ICD-9 codes that are associated with painful conditions, that could be a form of internal validation.
Absolutely, and we took the easy way out by asking the clinicians to, we also presented them with all of those, and then they would mention those out. So yeah, we used that, but we didn't directly sort of auto-validate. The other reason to be careful about auto-validation is when you're presenting this talk to a medical audience, it is much nicer to say, 3 clinicians validated this with me, rather than to say, I auto-validated based on internal things that were in the notes.
I would also point out, based on the discussion we're having, at our own institution, we started using this Dragon software, which allows us to speak, and it automatically kind of cleans up some of our language, and already itself has some transcription abilities. I wonder if that could be integrated with
Sure, yeah. I mean, Dragon has been used for, I had some tendinitis problem once, and I used Dragon like 10 years ago, and it used to work pretty clean now. I mean, most of us can speak to Google and Siri now and be perfectly understood. Google went from not understanding my accent, which by now is a weird mix of Indian and American accents, to being really 99.something% correct in recognizing me within 2 years. So when Google Voice first rolled out and I would say something, it would have no idea what I was saying. I would have to switch it to Indian mode and then speak with a pronounced Indian accent for it to recognize. Actually, so if you're correctly identifying it, it's not correctly identifies the fact that it's made the audience says there's no hallucination. Yes, yeah. Sorry. Yeah, go ahead.